I hope you all enjoyed your lunch. We're going to get going now. We've got 3 talks this afternoon. The first one from my predecessor as director of the Comet section, Jonathan Shanklin. And I asked him how long he'd been director for, and he said he couldn't really remember. It was something like 20 or 25 years. So I've got a long way to go to beat that. Jonathan's main job, though, has been in the British Antarctic Survey. He's the only person I know who's got a glacier named after him, the Shanklin Glacier. Woo! He's a recipient of the Polar Medal from Her Majesty Queen Elizabeth and has a Blue Peter badge. So Jonathan's going to be telling us about what we do with all of those observations you make, all of those visual magnitude observations. So Jonathan, over to you.
I shall try and keep you entertained to justify the applause that you've just given me. So let's see what happens. If I press that, we get on to the next thing. So we've already gathered that comets come in a variety of different sizes and shapes. And that's really quite important when we come to look at how they behave in terms of their total light output. I'll be mostly talking about the total visual or visual equivalent magnitude of a comet as we see it from the Earth. Most comet orbits are elliptical, either moderately elliptical or even near circular, as in the comet that Richard told us about. Encke is probably one of the shorter period comets with a period of about 3.5 years. And then other comets are either on fully parabolic or even hyperbolic orbits. With Comet Encke, because it has more or less exactly 3.1/3 years period, apparitions reoccur more or less in the same circumstances every 10 years. So 3.1/3 times 3 is 10. And this just traces some of the returns across the sky as you might see them from the Earth. So ideally, for a good view, we want a line that ends up this side of the line, because if they're on this side, you're looking towards the sun. So a good return would be one that comes over here. And an awful lot of returns for this comet are not that good. Now, if we want to work out how bright a comet is, we need to correct for the distance from the sun and from the distance from the Earth. So the distance from the Earth is this value, and that's purely geometry. So that should be relatively straightforward. The comet has an absolute magnitude, and that's how bright it would appear if it was exactly 1 AU from the Earth and from the sun. And then this parameter tells us how rapidly it brightens as it approaches the sun. There are other formulations, and some comets appear to brighten pretty much linearly rather than logarithmically as they approach the sun. So that just sort of gives the mathematical formulation. And I'm going to start by looking at a comet that has a lot of hype about it already, and try and explain some of that hype. So at the moment, it was discovered when it was still 7 astronomical units from the sun. That's a long, long way away, and it's moving comparatively slowly inwards. So today, which I think is what I did here, it's still over 6 astronomical units away. Still a very long distance. Even by the end of this year, it's over 4 AUs away. And then as we zoom in towards perihelion, it passes closer to us than the sun. In fact, inside Mercury's orbit is in this rendition. But it's not until it's a bit further outbound that we will get a reasonably good view of it. So this is mid-October, and the angle between the comet and the sun is starting to increase. And then a little bit later, it does actually get to be more or less exactly 1 AU from the Earth and the sun. So that is when we'll get a really good handle on its absolute magnitude. So what I've done here is plot all the observations up to roughly mid-June, and then take in chunks and try and extrapolate the magnitude into the future. So by the end of February, if I'd done a simple analysis, the comet would have been brighter than the sun at perihelion. That is clearly wrong. But the error bounds are even bigger. So it could be a sort of hypernova or a total damp squib. By the end of March, things are settling down a little bit. It still looks like the comet might be really bright, but still the error bars are huge, brighter than the sun or not visible in the largest telescopes. End of April, yeah, oh, it's gone brighter again. Now, why would that be? And the reason for that is a few of the electronic measurements are giving rather bright estimates for the total magnitude. And that's skewed the graph considerably. A little bit later still, end of May, still got a good fit, still quite bright. And to the end of June, it's suggesting that we take it at face value, -6, but still a range of -13 to +0. So a lot of scope for error. That's the best fit for using the 2-parameter fit. If I force one of those to be a pretty average comet, it gets a bit fainter, maybe reaching 0 magnitude, but still fitting the observations quite well. And if I take the average for all comets, which is about brightening with a K value of 8, it's only 2nd magnitude and still quite a big range. It might still be the case that it's going to be a faint telescopic object. So we really need to keep observing. And remember, this is the tail wagging the dog. So we're still a long way away from the sun. And really, please don't speculate as to how bright it will be, because the scientific evidence is just not there at all. What we can do, though, is say when we can see it, because the orbit is pretty well known. And so prior to perihelion, conditions are moderately good in the spring of next year. And then after perihelion, we get a window from mid-October through to the end of the year when conditions are moderately favorable. So not very high up in the sky, but at least it's an evening object and we do get to see it from the Northern Hemisphere. So fingers crossed, there'll be lots of observations. And it might be something like Comet McNaught in 2007, which was quite a nice object in the evening sky. It developed to be something rather more than that. Or it might be something like one of the current comets, which is visible at the moment, where it's just a fairly fuzzy object, probably visible in binoculars, but nothing terribly spectacular. This one was one that brightened much more rapidly than average, and that's why it's currently a small telescopic object. Now, for doing the analysis, traditionally, observations of comets were made with long focused refractors like this one at the Cambridge universities. But today, most of our electronic observers are using CMOS type detectors on average sized telescopes. And what we need to try and do is establish a link between the two so that we can use the old observations of particularly the periodic comets that have been made over many decades to link in with the new observations that are being made electronically. And we shouldn't just bin all those old observations because they were made visually. We need to be able to make use of them. So we need to establish the link for the long-term monitoring. Another problem is that with visual observers, in general, with a small pair of binoculars or with naked eye, we see a comet as being brighter than with a big refractor like the one I showed earlier, or a big reflector. And we need to be able to correct for that. And the work on that has been done over many years, and it's fairly well defined what the visual correction should be. The question is then, is there a correction that we need to apply for the electronic observations? And to try and work up on this, I used observations that were made of this rather nice comet that was observed electronically more or less after discovery, and then became bright enough for visual observation. So it reached probably about third magnitude. And this graph uses all the observations put together. One thing I will note is that for the electronic observations to be used, it's really important to report the coma diameter. That's because it helps to distinguish between a total coma magnitude and a purely nuclear magnitude. So if your observation is only that very central part of the coma, it's no good for comparing with the visual observations. So I don't use any electronic magnitudes that don't have a coma diameter associated with them. And as you can see, it's a moderately good fit, taking everything together, possibly a little bit different down there. And particularly when it's at its brightest, the observations seem to be quite a bit brighter than the mean curve. So if I just use the visual observations, we get similar parameters, slightly better fit at the top, but there's still something going on there. Was this an outburst of the comet, which is certainly possible, or is it just visual observers switching to smaller apertures and therefore reporting brighter magnitudes? So here I've used only the observations made more than 30 days before perihelion. And again, by and large, we get pretty good fit the whole time. Taking that as a basis, just in case there was an outburst when the comet was brightest, what I've done is see whether there's a correction that's needed for the aperture of the electronic observations or the aperture of the visual observations. And it turns out that you don't need to correct the electronic observations at all, which is really what you'd expect. They should be completely objective, whereas the visual observations have a subjective dimension to them. And it turns out that for this comet at least, the visual correction is broadly the same as what I determined about 30 years ago on one of the earliest comets that I analysed. So that was really reassuring that, yes, we can use the electronic observations. Yes, we can correct the visual observations to match. And so since doing this analysis, I'm now going to standardize not on the traditional 8-centimeter aperture, but on a 30-centimeter aperture, which matches pretty much the larger telescopes that are in use today. And making that correction, we now get a pretty good fit for the entirety of the light curve. There's possibly still something going on during that near perihelion period, but by and large, we're able to simulate the entire curve with just 2 parameters, which is what you try and do if possible to simplify things if you can. But not all comets follow that logarithmic style. There are a few that follow a rather different pattern, and where, because of the linear brightening, they turn out to be brightest usually sometime after perihelion. On this particular comet, over successive apparitions, the delay in intrinsic brightness has been getting longer. So it's currently about 85 days after perihelion, but if we go back several apparitions, it was a shorter time period after perihelion. But again, using that type of light curve, it gets a pretty good fit to all the observations, although there is quite a lot of scatter involved. One of the things that I think Helen mentioned in her talk was when you look at all the observations together, there's an awful lot of scatter. But it turns out, yes, observers are biased, but usually they're systematically biased rather than random bias. So an observer, there's in fact one particular observer always reports about a magnitude and a half brighter than everybody else. And there are other historic observers, Melvin Taylor, former member of the section, he always reported magnitudes that were about a magnitude fainter than everybody else. But the good thing about this is it's a Poisson type distribution. It's pretty much uniformly distributed about the mean. And that means it's random. So provided we use as many observations as possible, we can cancel out for this random bias effect in the observations, which again is really quite handy to be able to do that. Now, I've been writing papers on the comets of every year for a very long time now. I don't think I really expected when I did the first one that I'd be still writing them 30 odd years later, but I am. Originally, I described every single comet of the year because there weren't that many. However, with time, the numbers have increased. And in 2000, there were really quite a lot of comets being discovered. And today, there are not quite hundreds of comets every year, but well, there are if you count the SOHO ones, but there are an enormous number. So the more recent papers really concentrate on the brighter comets of the year. But each one of these papers gives all the available magnitude parameters for the comets that were observed during that year. And in the paper that I'm currently working on, I've gone through some of those, and I've also published in the recent BAA journal the results of all of this. So just to highlight some of that, this is the format that I've traditionally published the tables. In the latest paper, I'm also giving a measure of the goodness of fit overall, because I think that's quite a useful parameter to have. But when we look at the different types of comet, and here I've only looked at whether they're periodic or parabolic, we can see that there's quite a difference in the absolute magnitude of those comets. Because it was mentioned in one of the earlier talks that actually there are the two populations of comets, there's the Oort cloud comets and the Kuiper belt comets. I feel I really ought to redo all of this again and trying to distribute the observations between those types to see if there's a difference in the two populations. That will be an interesting scientific study. So it's on my to-do list, and I will get onto that. But we can see that generally the periodic comets have a somewhat fainter absolute magnitude than the parabolic ones. Some of that will be historical, because in order to be discovered, the comet had to be in a good combination of observing circumstances. And because with a periodic comet, you get lots of goes at it, they are perhaps slightly more likely to be discovered than a parabolic comet, where you only get one chance at discovering it. So that may partly underlie that difference. When we look at how rapidly they brighten, the parabolic comets average out at about 8, and if you take the whole lot together, it averages out at about 10, which is why I was looking at those two values for Comet 2023A3. And I think until we have more data, I'd continue to use that log 8 log rather than anything else, because that's going to give us the best guess at the moment. When it comes to peak activity, so this is using the linear type of light curve, there's a definite bias towards being brightest after perihelion. That in some ways is understandable, because on the Earth, temperatures are usually warmest not at noon, but perhaps an hour after noon. Similarly, in the summer, temperatures aren't warmest on the solstice, which we just had, but a month or so after the solstice. And so we should expect comets broadly to be behaving the same way, that the energy release is going to be greatest perhaps a month or so after perihelion. And the evidence certainly suggests that comets do that. What is slightly baffling is how some can be, if you like, even years after perihelion, which seems rather unlikely, unless some very unusual physics is going on. But these are just presenting the observations as they stand. I'm not interpreting them in any way at the moment, but it may be interesting in the future to see whether the shape of a comet makes any difference to how its light curve behaves. So 67P has a very complex shape. Is that reflected in the light curve? Now, some comets seem to repeat pretty much return after return, and you can paste on top of one return the observations at the next return and see a similar sort of behavior. So 6P Dara-S, more or less apart from this shift that I mentioned, is a repeating comet. It's pretty well behaved. One of the longest observed comets that we have is 2P Encke, and there are section observations going back to the 1940s. It's one of the first comets that we've got decent observations on. And taking the absolute magnitude, this time using a forced value of 15 for the rate of brightening, we can see whether it's changing. And if you just look at the error bars, a null hypothesis is tenable in this, that there's no change, but the best fit suggests a slight fading. However, in the Cometographia series that Gary Cronk has written in conjunction with Mike Mayer, there are observations for all the returns based on, oh, I forgot what his name is now, Veshkahaski or something unpronounceable Russian like that. And so if I add those in, the observations do really fit a long-term decline in the brightness of the comet. And that seems pretty clear cut. Although here I've just used a linear fit, I could use a third order type fit. And that might, if you've got a bit of imagination, suggest that the decline has leveled off. It's another case of we need more observations. So everybody do go out and make observations of Comet Encke. We'll see how it behaves in the future. Another comet where even the fairly limited data set shows a distinct decline is Kearns-Cui. That is really declining very rapidly. So in 50 odd years or 60 years of observations, its absolute magnitude has dropped by around about 4 magnitudes. So that is really quite a significant decline. The one comet that we've got really good in situ measurements of, and which is really quite important, unfortunately doesn't behave itself very well when it comes from one return to the next. There are quite substantial differences in the brightness. And the question is why? It could be that the comet's nucleus is precessing and different parts of the comet are being exposed to sunlight at each return. It could be erosion, and that's changing the shape of the comet from return to return. But those are all speculations. I think what we will need are future spacecraft to go and visit it again to see how it's changing. Initially, when I did these analyses, I thought, well, the perihelion distance of the comet changes, and the absolute magnitude of the comet is changing with that perihelion distance. The most recent one was this one, where the comet was the closest it's yet been to the sun at perihelion. And I was predicting it would be up here in terms of absolute brightness. Unfortunately, it turned out the observations put it down there. And so a link with changing perihelion distance, at least for this comet, remains an open question. The best fit graph, the line does suggest that, but equally the null hypothesis is still a tenable one. And I think for simplicity, we should assume that there's no change at the moment. 19P Borrelli is a larger object, and perhaps for that reason, the light curve is much more repeatable from one return to the next. So I think we're on possibly some hints that it may be shape of the comet and size that is governing some of this variation. So concluding, it's really quite important to know that the visual and visual equivalent magnitude observations that you make do give physical insights into the cometary nucleus. And there are changes in the absolute magnitude of many comets with time. And this may be surface erosion, precession, evolution of the perihelion distance, evolution of the active areas, as Richard was saying for comet 29P, there's changes in which areas are active, or indeed fragmentation events, which we know happen in many comets. There may be splittings, there may be large lumps breaking off. And coming from the Antarctic, glaciers evolve in a variety of ways when they reach the sea. Most of the erosion is in small bits, but every now and again, there's a really large event that sends a big iceberg out to sea. A really important point is that the visual equivalent magnitudes extend the light curve way beyond what a visual observer can do, and to many comets that are simply too faint for the visual observer. So there's a paper in the June journal which describes some of that work. I'm working on another one at the moment, which I hope to be able to send formally to Nick later this week with a bit of luck, because I've got most of the information I need for it. And that will be the brighter comets of 2021. And then I suppose how to start working on the brighter comets of 2022. Thank you.
Thank you, Jonathan. And I'm extremely grateful as section director that you do these brighter comets or these annual summaries. It's a fantastic archive of observations. And I think one of the things that really sets the BAA out, that we actually do use our observations and do analysis of them. So I think we've got time for one or two questions to Jonathan. Anyone got any questions?